Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are going to start the 13th lecture of Discrete Structures CSC 102. In previous lecture we have studied method of proofs, in which we have studied mod functions, mod relations and mod congruence. We have studied also the method of indirect proof, which is a method of contrapositive, and we have also studied method of contradiction, the relationship between method of contrapositive and contradictions, and at the end we have seen some classical theorems. Now we are going to start set theory. In this today's lecture we see what are the sets and the major operations: intersection, union, complement and subtraction of sets. We shall also see some the operations of set. We shall see by using Venn diagrams, with the help of Venn diagrams. Now, why we study the set theory? Set theory basically help us to systemize the things and organize the things into the groups, and we will be able to understand better the properties of logic. So what is a set? Set is basically a collection of objects. The objects must be defined and distinct. The elements of the sets are usually called members or elements. The sets can be of anything, for example, numbers, people, letters, alphabet letters, and many other things. Sets are conventionally or usually denoted by capital letters. The one thing you should remember, that in sets the objects must be distinct. Distinct means they are separated and well defined. For example, if we take up the examples in the next slide, the first example is the set, which is a collection of large species of cats. For example, tiger, lion, puma, cheetah, leopard, cougar and ocelot. So these are the special kind of a species, which is the large species of cats. So in this collection we have objects which are distinct and defined. So this is basic, and this is denoted by capital letter A. So this is a set. So another example in which we take the set A or B, whatever, we can denote it by any other letter, capital letter, which is basically the set of alphabets, small letters of alphabets of English, A, B, C, D up to Z. So these objects are also separated, distinct and defined objects. The sets can be of the numbers. For example, we have -2, -3, and so on. So this is basically a collection of numbers which are distinct. Distinct means they are different from each other and well defined. So this is another example of set which contains the numbers, means the members of the set or elements of this set are negative integers. So in all three examples, the elements of the sets are separated, distinct, and they are well defined. So by the definition of set, a set is a collection of objects which are well defined and distinct objects. Set can be finite, infinite. We will study all these concepts in the subsequent slides. Now we see the operations on sets, just like we do the operations on numbers. For example, we add up numbers, we subtract numbers, we divide, multiply, These are the algebraic operations on numbers. Similarly, we have operations on sets, and these operations are basically union, intersections, complement, and subtraction of sets. You have already studied in earlier classes 6, 7, 8, 9, 10 the union and intersection of sets. We'll see quickly here what is the union and intersection on sets. If we have two sets A and B, for example capital A and capital B, which contains distinct and well-defined objects, how we take up the union of two sets? The union of two sets is basically denoted by A union B. You all I think you all should already know this. The union of two sets A union B is basically a new set, is another set which contains or the members of this set are the members of either A or B. Means we add up all the numbers of A and B, and we avoid the repetition of members of A and B. For example, if we have two sets, A is the set 1, 2, and B is the set red, green. This is the set B. And if we take the union of these two sets, 1, 2 union red, white, then in union we write all the elements of A, all the elements of B, but we avoid the repetitions. For example, in second example, if we have this set A, the set B. In set A we have 1, 2 green. In the second set we have red, white, green. So this is a set of names of color, you can say. If we take up union, we write 1, 2 green, 1, 2 green, and red, white, green. Green here comes 2 times, so we write only 1 time in union the member green. So we avoid a repetition in the union, but we write all the elements of set A and all the elements of B if there is no repetition in these two sets. If we have the union of a same set, for example A union A, this is always the same set A because we avoid the repetitions here. If for example in third case, if we write 1, 2 union set 1, 2, it remains 1, 2. So this is how we add up the sets, or we take the union of two sets. Now the intersection of any two sets A and B, if we take up two sets A and B, then in intersection we take, intersection is basically another new set which takes only those elements in both sets which are common. For example, the intersection of these two sets, in the second example, this intersection of these two sets will be a new set which contains only green. So in intersection we take up only those elements which are common in both sets. For example, the intersection of A and B is usually denoted by A intersection B, and it is read as A intersection B. You have already studied, I hope, in earlier classes. Basically this new set is contains those members of A and B which are in both A and B. If the intersection of the two sets A and B is contains no common members, then we say that intersection of A and B is equal to empty set. An empty set is usually denoted by these two brackets like this, or a symbol which is phi. You already know this, I hope. This is the symbol for this is exactly written as this, and this is basically the phi set or empty set. If there is no common member between A and B, then we say that A intersection B is empty set. It is usually denoted by this or this. And we say that the two sets A and B are disjoint. So two sets, and if for example if we see this example, we have one set 1 2 and the other set is red white. The intersection of these two sets have no common elements. As these two sets have no common elements, then we say that it's the intersection of these two sets is an empty set. Another example, the second example, the same as we have seen on previous slide. If we take up intersection of 1 2 green, intersection red white green, so there is only one common element in these two sets, which is green. So in intersection we have green. So intersection of a same set with the set A, intersection A is always A, as we have seen in the case of union. If we have same set, intersection of A with the same set remains the same set. So in intersection we take up common elements, those elements which belongs to A and which belongs to B. So this is what we do in union and intersection. The next is the subtraction of two sets, or we can say the complements. Two sets can also be subtracted, as we have added up two sets and we take up the union of A and B. Similarly, we can subtracted two sets, and we say that the relative complement of B in A, this means A minus B, or we can say also it set theoretic difference of A and B, and we denote it by A minus B, the relative complement of B in A. This is not the usual complement which you have studied in earlier classes with respect to the universal set. This is basically the difference of two sets, or we subtract one set from another set, the relative complement of B in A. This is denoted by A, this bar, this basically this bar is used to denote the difference. This means A minus B denoted by this A minus B, or we can denote it A minus B is the set of all those elements which are member of A but not the members of B. It means the common members which are in A and in B we subtracted. We eliminate those those members from A which are in A and also in B, and the rest of elements will come in this set A minus B, or in this set. For example, if we have this example 1 2 green minus red white green, so green is common in these two sets and we are subtracting B from A, so we write only those elements of A which are not in B. So this is basically A minus B, or A minus B. So here we take a note that is valid to subtract members of a set that are not in the set, such as removing the element green from the set. This doing so has no effect. What does it mean? That red and white are in set B. Even if we subtract red and white from this set, there will be no effect, because we subtract only those numbers which are common in both sets, and the rest of the members which are in B we leave them. A minus B actually contains only those elements which are only in A but not in B. So the only elements which are the elements which are only in A are 1 and 2, so we write A minus B is 1 2. the common members will be eliminated from A. So for example, in this slide, in this example, if we subtract red white from 1 2, because there is no common element here in these two sets, so the A minus B becomes A. Basically A minus B becomes A when we have no common elements in A and B. So another example, if we subtract same set from the same set, A minus A is basically the empty set, because they have all the common elements in both sets. In the next example, if we take up if U is the set of integers which contains positive integers, negative integers, even number, odd numbers, and E is the set of even integers, O is the set of odd integers, then E complement is O. Or you have already studied what is the complement of a set with respect to the universal set. U here is basically the universal set, E is its subset, O is its subset, and then the complement of E is O, and complement of O is basically E with respect to the universal set. So this is what the complement which you have already studied. Now the Cartesian product of two sets. Cartesian product of two sets is basically a new set. A new set can be constructed by associating every element of one set with every element of another set. So this is how we construct the Cartesian products, as by the name product. So we take here the product of two sets, and product Cartesian, and it is called Cartesian product of two sets A and B, as I have mentioned here. It is denoted by A cross B. Sorry. Cartesian product of A cross B, A and B, is denoted by A cross B, and it is basically the set of all ordered pairs AB, such that A is a member of A and B is the member of B. For example, in this first example, if we have two sets A, for example, the set A is 1 2, the set B is red white. So what is the Cartesian product of these two sets? How we write it? We write the first element of first set, first with first, first with second, as in ordered pair. In a pair, we write first element of the first set and the second element of the set on the second place. This. Similarly, we take up 2 with first element, 2 with the second element, 2 with red, 2 with white. So the first place on this ordered pair is always we write those sets which belongs to the first set A, and on the second place we write the elements of the second set B. So this is how we write the Cartesian product of two sets. For if we take up another example here, we have 1 2 green, red white green. So we write 1 with red, 1 with white, 1 with green in the ordered pairs, 1 red, 1 white, 1 green, and then we choose the second element, 2 red, 2 white, 2 green. Then we choose the third element, green red, green white, green green. So this is how we write the Cartesian product of any two sets, any two finite sets. In this example, we take up 1 with 1, 1 with 2, and then 2 with 1, 2 with 2. So this is how we write the Cartesian product of two sets. Next, special sets. There are some we take another example of for example the Cartesian. We can take another example, but I hope you understand how we write the Cartesian product of two sets. Next we take up the special sets. In mathematics there are some common sets which are well defined. These sets have some special notation and convention to identify them. For example, first of all, the usual set, empty set, is denoted by two empty brackets or this notation. Another is a singleton set which contains the only one element. So these sets are most common sets which we used, and you have already studied in earlier classes. There are some sets which have special notation. For example, P, the set denoted by capital P is the P letter, you can say, is only allocated for the set of prime numbers. If somewhere in the books you see the set capital letter P, this means obviously that this is a set of prime numbers, and you have already studied the prime numbers in the previous lectures. So set of prime numbers is basically 2, 3, 5, 7, 11, 13, 17 and so on. So this is basically an infinite set. Similarly, you can take up the capital N, the set of natural numbers, which is always denoted by capital letter N, which denote the set of natural numbers, and this set contains 1, 2, 3 and so on. So this set also has some special notation, capital N. Similarly, the set of integers Z, it is denoted by capital Z, and it contains elements you already know, I think, plus minus 1, plus minus 2, plus minus 3 and 0 also, and this is basically the set of integers, and this set is also have special notation Z. Another set is Q. Basically, Q is the set of rational numbers. It is always denoted by capital Q, which contains the numbers of this type. We have already studied this, A by B, where A, B are integers and B must not be 0. For example, 1 by 4 belongs to Q and 11 by 6 belongs to Q also. So these are sets which are famous sets, and they have special notations. There are some other sets. For example, the set of irrational numbers is usually denoted by Q dash or Q complement or Q bar. So usually denoted by usually these notations are reserved for set of irrational numbers. There is another set which is the most famous result in calculus, in every field of mathematics, the set of real numbers. It is usually denoted by capital letter R, or sometimes like this. This set denotes the set of real numbers, which is basically the set of real number is the union of rationals and irrational. It contains all the numbers on a straight line, you can also say. Another set, very famous set, which is the set of complex numbers, which contains the complex numbers a plus I, b or bi, where this I is in mathematics, in complex number, is called iota, and this iota is basically equal to square root of -1. So such type of numbers are called the complex number, and the set of complex number is usually denoted by capital C. So these sets are basically the special sets. These have some special, or you can say that some particular type of numbers, and they have some particular type of notations also. So avoid I recommend you to avoid to denote the sets other than these sets. don't use these numbers to denote other sets, because these are the reserved sets and reserved notations for these sets. Now the finite and infinite or infinite sets. Finite set, as usually you can guess by the name of this set, finite set, a set which contains finite many elements is called a finite set, and a set which contains infinite many elements is called a infinite set. For example, we have studied the sets in this slide. A set 1, 2 is a finite set, whereas the set of prime numbers is an infinite set of natural numbers is an infinite set, z of integers is also infinite set. So these are all infinite sets. For example, you can take the number of digits on your hand. For example, when you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so these numbers which you can count on your hand is basically a finite set. The number of seats on a bus is also a finite set. The number of people on earth, this is also finite, because we can count these people, the people on earth, no matter how large the number of people is on earth, but we can even then count those people. So these are the examples of finite set. Infinite set is the set of rational numbers, set of whole number. Set of whole number, I hope you know what is the whole number. It is denoted by W, and it contains 0, 1, 2, 3 and so on. So this is another set, the set of whole numbers. It is usually denoted by W, capital W. So this is also a special notation for this set, so please avoid denoting other sets by capital W. So these are the examples of finite and infinite sets. Another thing which is called cardinality. Cardinality is basically the number of elements in a set. Cardinality denotes the number of elements in a set. For example, if we have this set A, it can be written as x such that x is a lower case letter. So this is another notation or notation of a set. We can write set in different forms. You have studied in earlier classes that we can write set in a descriptive form, in a the other name in a descriptive form, that is we can write in English a set A which contains the elements which are case letter, or we can write the letter in this form also. X is A is a set which contains the elements X such that, now this bar means such that means this X satisfies this condition. This is what we can understand here in this notation of the sets. It's set A which contains the elements X, where such that X, the description of X is given here. What is X? So X is a lowercase letter. So this set basically is the set of small letters of alphabets, means A, B, C and so on up to Z. So this is basically the original set, because we have written this set in the descriptive form where X, such that we have mentioned here X is a lowercase letter. Instead of writing all these letters, we write the set in this form. And what is the cardinality of this set? How many elements are there in this set? And we know that there are 26 small alphabets of in English, so the cardinality of this set is 26. Cardinality of this set is 1 2 3 4 5 6. So this set contains 6 elements, so the cardinality of this set is 6. So cardinality of finite sets is basically the number of elements in that set. This is called the cardinality. So if we take up this set X such that X is an even number less than 10, so what elements this set contains? Here C contains X elements such that X satisfy this condition, so all numbers which satisfy this condition will be in this set. So X such that X is an even number less than 10, so this is 2 4 6 8 8, because 10 cannot come here, which is here we have less than 10, so this set contains these 4 elements, so the cardinality of this set is 4. Now there are some infinite sets, for example A, which contains infinite many elements, 1 2 3 and so on. This is basically the set of natural numbers, and we know that for the time being you remember that the cardinality of set of natural number is denoted by this this symbol, and similarly the cardinality of set B, X such that X is a point on line, this is also an infinite set. Then the cardinality of this set is also these sets are infinite, but their cardinality is denoted by this symbol, similarly for this set and similarly for this set. So this is a cardinality. About the cardinality we shall study what is the cardinality and why we take up the cardinality of infinite set, the set of natural number, as this number, and we'll study about it in the next lecture. For the time being you remember that the cardinality of set of natural number is this symbol. Now the memberships and or some notations about the sets. The relation between sets is the membership. What elements belongs to what set, or which set is a subset of which set contains this set. So such type of questions we shall discuss in this topic of memberships. So if A is a member of B, this is denoted by A belongs to B. So this is the membership of elements to the set. If we say that this a particular member A, for example, is a member of B, then we denote it by A belongs to B. And if we say that a number C, any number, is not a member of B, C is not a member of B, then we denote it by, in set theory, C belongs, and we write a bar on this. We take it, this means belongs, and if we cross it by a bar, it means C doesn't belong to B. If C is not a member of B, then mathematically or in set theory we write it as C doesn't belong to B. For example, with respect to sets A and B, 4 belongs to A and green doesn't belong to B, and it read as green doesn't belong to B because green is not in B set. So this is basically the membership. We'll study further also the inclusion of sets and many other properties of sets. Next, what is the universal set? Basically, a universal set is the set of all things, all objects relevant to a given discussion of sets, and is designated by, or it is denoted by a capital letter U. It contains every set under consideration. For example, if we have sets A, B, C, and we are trying to find A intersection B, A union C, whatever the operations we are requiring to make on these sets. The universal set basically contains all these sets. So universal set is basically is a set which contains all the sets under discussion or under the manipulation of sets. So such type of set is called universal set. Subsets: if every member of a set is also a member of another set B, then A is said to be subset of B and written as A is subset of B. Also pronounced as A is contained in B. The relationship between sets established by this symbol is called inclusion or containment. So subsets, I hope universal sets and subsets you already know, and you can quickly understand these things. If we say that A is subset of B, what does it mean? It means that every element of A is also the element of B, or every member of A is also the member of B. For example, A, here we have taken A, B. A is subset of B because 1 belongs to A, 1 belongs to B, 2 belongs to A, 2 belongs to B, 3 belongs to A, and 4 belongs to B also. So every member of A is also in B. So A is subset of B, but B is not subset of A because there are elements in B which are not the members of A. So B is not the subset of A, and we denote it by this symbol. Now the proper subset and improper subset, what is this? We'll study, I think, this here. Now what is the proper subset or super subset? First of all, superset. If we can write B contains A, read as B is superset of A, or B includes A, or B contains A, then B is called superset of A, and A is called subset of B. In previous examples we have seen here A is subset of B, B is superset of A, means A is subset of B and B is superset of A. Super means he is larger than A and A is smaller than B. So this is basically, I hope you have already studied this. So proper subset, now A, if A is a subset of B, here I must write B, but not equal to B, then A is called a proper subset of B, and it is written as A is proper subset of B and read as A is proper subset of B. Here in this notation here we have written A is subset of B, but it may be equal to B. This symbol, the line under this symbol shows that A may be equal to B. For example, if we have A this and we have B, again 1 2 3 4, then in this case A is improper subset of B, means A may be equal to B. But here in this case B contains 2 extra elements than A. In this case A is proper subset of B, means B is superset of A, and A is proper subset of B because B has 2 extra elements, 2 other elements than A. So in this case we say that A is proper subset of B, or B is proper superset of A. Similarly on the same thing, for example, this set is a proper subset, but this set is not the proper subset. This is called improper subset. If a set is not a proper subset of another set, then this may be improper subset of the other set. Now what is the power set? But before this we take up a simple identity which is very useful in sets and in method of proofs, and if we want to prove the inclusion and inclusion of sets or equality of sets. Two sets are said to be equal and written as A is equal to B if and only if A is subset of B and B is subset of A. So in order to prove two sets to be equal, we always prove that A is subset of B and B is subset of A. If we are succeeded in proving A is subset of B and B is subset of A, it means that both sets must be equal. So this identity we'll use oftenly in the next subsequent slides. Now what is power set? Power set, I hope you all know what is the power set. The power set of a set A is the set containing all possible subsets of A, including the empty subset and the set itself. So if we want to write the power set of a set A, B, C, D, then what is the power set? It contains all possible subsets of A, including the empty set. So first of all, to write the power set, we write the empty set. Empty set, then we write each element of that set one time, singleton sets. Then we take up two elements, AB, AC, AD, and then with B, BC, BD, and C, CD, and then we take up three elements, ABC, ABD, ACD, BCD, and then the set itself A. So the proper set, the super power set contains the empty set and the set itself also. Other than this, we take up all the possibilities of the subsets of A. Now how many elements are there in the power set? The power set always contain, this is denoted by P of A or 2 power A, and it contains the 2n elements, 2n, where n is basically the number of elements in A, n is number of elements in A. Here in this case, what is the number of elements in the power set of A, where A is A, B, C, D. So the number of elements is 2 power 4 because there are 4 elements in A. 2 power 4 is basically 16. So in the power set of A, we must have 16 elements, so which we can count by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. So there are 16 elements in the power set of A. So this is how we can calculate the elements in the power set. So the next is subset relationships. What is the subset? If we have this set A, where A contains elements x, such that x is a positive integer less than or equal to 8. So it contains less than or equal to positive integers less than or equal to 8, which is 1, 2, 3, 4, 5, 6, 7, 8. B is the set which contains elements x, such that x is a positive integer less than 10. So this contains 4 elements, 2, 4, 6, 8, 10, 8. C is this set 2, 4, 6, 8, 10, and we take up another universal set. Now subset relation, A is subset of A. This is always true. Any set is always the subset of itself. A is not subset of B, we denote it by this. A is not subset of C, we denote it by subset, and we cross it. This is basically the notation of not subset of another set. So next is B. We can see B is subset of C, B is subset of A, sorry, B is subset of A, B is subset of B, B is subset of C. C is not subset of A because C contains 2, 4, 6, 8, 10, but in A we don't have 10. Similarly, C is not subset of B and C is subset of B. So these are the subset relationships we can see by using these sets. Now set equality, as we have discussed earlier, that two sets are equal if and only if A is subset of B and B is subset of A. So two sets are equal if and only if they contain precisely the same elements. There must be exactly same elements in two sets to be equal. The order in which the elements are listed is unimportant. The order, for example, if we take A as 1 2 3 4, B is 1 4 2 3, then these two sets are equal because they contain exactly same elements and exactly same number of elements. The order of elements, we can interchange elements in the sets, no matter even then the sets are equal, because A is subset of B and B is subset of A. Here this is improper subset, not the proper subset. A is improper subset of B and B is subset of A, therefore A is equal to B and B is equal to A. We can write it as. Similarly, this A set 1 2 2 3 4 1 2 and B is 1 2 3 4. Here we have 4 elements, here we have 4 elements, but the 2 elements, this is repeated 3 times. Even then, elements may be repeated in set definition without increasing the size of the sets. So the size of cardinality of this set is also 4. Cardinality is 4. They have exactly same elements, so A is improper subset, therefore A is equal to B and B is equal to A. So this is how we see the equality of two sets A and B. The next is, we have used some notations in the set theory. Uppercase is designates set name, lowercase designates set elements. This basically, these brackets are used to enclose the objects in the set, elements of the set. This notation denotes is an element of or is not an element of this. This notation is used for improper subset. It may be equal, it may be proper. This set is particularly used for proper subset. This notation is used for not subset of. This is a superset of. This bar or this symbol is used for such that if a condition is true, and this notation is used for cardinality. For example, cardinality of A is the number of elements in that set. So these notations we use in set theory. Now we start the Venn diagrams. So what is a Venn diagram? Venn diagrams or set diagrams are basically diagrams which shows the relationship between sets and their elements. The Venn diagrams also shows the intersection, union, complement and other operations on sets also. So therefore Venn diagrams show relationship between sets, their elements, and between their and between the sets also. We can also express using these diagrams operations on sets. For example, union, intersection, complement, and there are other operations we can perform using these diagrams. We'll see in the subsequent slides and in the next lecture. So how do we construct such type of diagrams? For example, you are watching a diagram in which we have one circle which represents the set A, the other blue circle which represents the set B, and a square which contains these two sets. This is basically the universal set which contains all the sets. So in Venn diagram we represent a square. We have this square which is basically the universal set, and the universal set contains all other sets which are under discussion or on which we have to define the operations. So this is if we have two sets, we write two sets, we made two circles. If we have three sets, we make another circle which represent the set C, another circle which represents the D, and then we can and so on. If we have two sets, three sets, four sets, five sets, and so on, no matter how many sets we have, we construct the bigger Venn diagrams to show the relationship between sets or their elements. The main thing is that, I repeat here, this square, this which contains all the sets, is basically at the back, which is the universal set. Now, if, for example, how we express these two sets using Venn diagram. If the first set is A, which is basically which contains X, such that X belongs to Z plus. Z plus means it is a positive integer, and X is less than or equal to 8. So it contains 1, 2, 3, 4, 5, 6, 7, 8. B is the set which contains the elements X, such that X belongs to Z plus. X is positive integer, and Z negative is denotes basically the negative integers. Z positive means positive integers. X is even and X is less than or equal to 10. So this contains these elements 2, 4, 6, 8, 10. Now we have to express these two sets using Venn diagrams. For set A, we made a circle. First of all, we see that if there are some common elements in A and B or not. So we can see that 2, 4, 6, 8, these are common elements in these two sets. So we draw two circles and we keep here some portion of these two sets common, where we can write the common elements. For example, here the common elements 2, 4, 6, 8, they will come in this common region. In this common region, this region is common in both sides basically, because this is in B and this is in A also. So the common elements come in the common region, and the elements which are not common, which come in the region which is not common in both sets. So this set basically represents A, this set represents B. So we write 3, 5, 7, anywhere we can write here 1, 3, 5, 7 here, because these elements are not common with B. Similarly, in B, the 10 element is not in A, so we write it here, which is not the common area of A and B. But the elements which are common in A and B, we write in common region this. So this is how we can write these two sets A and B using Venn diagram. So universal set is basically the set which contains A and B both. It could be, universal set could be here any set of you can say natural numbers, the set from 1 to up to 10. This could also be a universal set, but here we don't need what exactly is the universal set. Another example of this, how we express these two sets using Venn diagram. A is the set which contains basically 1 to 9 elements. B is the set which contains 2, 4, 6, 8. Now every element of B is also the element of A. It means B is proper subset of A. B is proper subset of A. We can see here. Now B is proper subset of A means B is contained in A. So how we construct the Venn diagram here? B we constructed here, and A must contain B, because A is superset of B or B is subset of A. Then A must contain B. So therefore we draw a small circle which represents B, and we draw a large circle which contains B. Now in B we write those elements which are in B only. 2 4 6 8, these are 2 4 6 8. Now outside of B we write those elements which are in A but not in B. 1 3 5 7 9. We can write anywhere these elements in A but not in the circle of B. So this is how we can construct the Venn diagram in which one set contains the other set. Another definition, another example, if we have two sets A and B, A contains 2 4 6 8 9. Now here 2 4 6 8 10, we must write here 10. So A contains 2 4 6 8 10 and B contains 1 3 5 7 9. Means this set contains even integers less than or equal to 10, and this set contains odd integers less than or equal to 10. So now there is no common region, no common element in these two sets. Then how can we express using Venn diagram these two sets? We write two sets A, two circles A and B, and we keep some common region in these two sets, this. But as there is no common element between these two sets, so this region remains empty. A contains 2 4 6 8, they will come 2 4 6 8 10 here, 1 3 5 7 9 here. Because they are not common, we can construct the Venn diagram like this, or we can construct the Venn diagram like this also, where U is this, A is this, B is this, A is this, B is this. Because A and B are disjoint sets here, there is no common element in these two sets, so the Venn diagram could be like this or could be like this. So these are both, we can express these sets using Venn diagram either like this or like this. We do not write the common, we don't write any element in the common region, or we can separately construct two sets A and B. Here we can write 2 4 6 8 10, here we can write 1 3 5 7 9. So these are two separated or disjoint sets. The next is set operations and Venn diagrams, how we can express the intersection of two sets and the union of two sets using Venn diagrams. As we know that intersection of two sets A and B is basically this contains those elements of X which are in A and also which are in B. In union, A or B basically contains those elements which are either in A or in B. This is basically the conjunction, this is disjunction as in logic. So set operation, in this using Venn diagrams, how we express the intersection, we construct a common region as we have studied in the seen in this example. In this example, this is basically the intersection of, this is basically the intersection of this region is A intersection B. How we express the intersection, we express intersection like this. Basically this is a common region of A and B, and the intersection of B is only this region. This is not A, this region is not, it's in intersection. This region is not also in intersection. Intersection of A and B only contains this region, So this, for example, if we have two sets A which is 2 4 6 8 10 and B is 1 2 3 4 5 6 7 8 9, then what is the Venn diagram of these two sets? It's basically intersection, union, universal set is this is set A, this is set B. So intersection, in intersection we have 2 4 6 8. So this is basically A intersection B, this set. So this is how we express intersection using Venn diagrams. Similarly, we can express the union. Union basically, the Venn diagram which expresses the union, it contains all elements of A, all elements of B. So this is basically the union of two sets. This area we can express the union of two sets using Venn diagram like this. Now, what is the difference of two sets? How can we express the difference of two sets using Venn diagram? This is how B minus A. This is B minus A. We can express B minus A like this. This basically, if we have this set is B, this set is A. Now if we subtract A from B, then all the elements of B which are also in A, those elements will be eliminated from this set, and we are left only with this set. This is basically A minus B. This set is basically B minus A. So this is how we can express B minus A using Venn diagram. Now, the complement of a set. How can we express a complement of a set using Venn diagram? If we have a set A, for example, 1 2 3 A 1 2 3, and the universal set is 1 2 up to 10, then the complement of A will be basically U minus A. If this set is A, then AC is basically the whole region which is other than A. This is the complement of A. This is how we can express the complement of A using Venn diagrams. Next, we see we take another example. How can we place elements in the Venn diagram? If we have set A, set B, set C, and universal set U, where the U is the set this. How we can place the elements in the Venn diagram? If we have three sets A, B, C, and this is basically A set, this is B set, and this is C set. So how we place the elements in the Venn diagram? First we see one is in A, one is in B, one is not in C. So one will come where we have the intersection of A and B, means where A and B have common region. So one will come here because here we have A and B common region. So next is 2. 2 is in A, 2 is not in B, 2 is not in C. So 2 is only in A. So 2 will come here where there is no common region of A and B and C. Next we write C. The 3 is in A, 3 is in B, 3 is also in C. So 3 we have to put in that region where we have a common region of A, B and C. So this is the only region which is common in A, B and also in C. So we put 3 here. Next we have 4. 4 is in A, B, C. 4 is not in B and C. So 4 is only in A, so we write 4 here. Next we have 5. 5 is only in B, so 5 will come here. Next 7. 7 is in B and C. So we see what is the common region of B and C. So this is the common region of B and C, so 7 will come here. Next we have 9. 9 is only in C, so 9 comes here. Now these are the placements of integers or members of A, B and C. Now we see the placement of the universal set. In universal set, 1 is already been placed, 2 is also been placed, 3 is placed, 4 is placed, 5, 6. 6 is an element which is not in A, B and C, but 6 is in universal set. So we write 6 here outside all these 3 sets A, B, C, because 6 is in universal set. 7 has been already placed. 8 is another element which is not in A, B, C, so 8 will come somewhere here outside the 3 sets A, B and C. 9 is already been placed in C. So we have placed all the digits, all the members of set A, B, C and U in the Venn diagrams. This is how we place the elements of sets in Venn diagrams. So this is basically the solution of the previous example. Next, how we sketch the region representing sets. For example, if we have this set A union B complement intersection C, we have 3 sets. How we can sketch or how we can mark the region corresponding to this set? First of all, we have to take A. A is basically this set. This set A is this whole set. We take the union of A with B complement. Now what is B complement? B complement is that region other than B. So this is B. The B complement is the whole region with respect to U. We are taking the complement with respect to the universal set. So this is the whole region which has B complement. So if we take up the union of these 2 regions, what we will get? We'll get this region. So this is our A union B complement, the whole region which is colored in blue. Now we have to take the intersection of this region with C. So what is C here? C is this whole region. This whole region is C. Now we have to take the intersection of this region and this region. So what will be the intersection of these 2 regions? We take this region, this region will be, only this region will be the intersection of these 2 regions. So we obtain this region as the intersection of A union B complement and C. So this is basically the region which is required, which represents this set or this expression. So this is how we can sketch or mark the regions which represents the given sets. Today we have started the basic set theory, and we have studied the definition of sets. We have studied also the basic operations, which are intersection, union, complement, subtraction, the usual basic operations on sets. We have seen also the memberships, how we denote the inclusion and the elements of sets, and we have defined also some notations in set theory. We have also studied the Venn diagrams, how to represent sets and their relations, the operations, intersection, union, complement of sets using Venn diagrams. In the next lecture we shall study some other operations and some laws of sets using Venn diagrams also. So for today it is enough, and we We'll meet in the next lecture. Until then, Allah Hafiz.